Section: Introduction. In this section, we introduce the significance of large language models, LLMs, and their growing role in various systems, such as providing supervision, aiding decision-making, and functioning as controllers in agentic frameworks. Understanding and predicting their behavior is essential, especially in critical situations. However, comprehending these large models is challenging, as traditional methods like input gradients and saliency maps often fail to accurately describe their behavior. We note that some research has explored how transformers can represent specific algorithms related to their predictions. A promising approach to understanding LLMs is to utilize their capability to interact with human queries. Recent studies have shown that the hidden states of LLMs can reveal features related to their truthfulness or harmfulness. Other research has focused on learning sparse dictionaries and analyzing how these networks respond to related input tokens. Despite progress, these methods typically require white box access to the models, which is not feasible for many top-performing LLMs that are only available through closed-source APIs. This leads us to question how effectively we can predict LLM behavior with only black box access. In our work, we propose a method to extract useful representations for predicting the performance of black box LLMs by querying them about their outputs. After receiving a prediction from an LLM, we utilize its ability to reason about its own answers and respond to follow-up questions, such as asking for an explanation of its answer. We hypothesize that the distribution of answers to these questions varies significantly based on the correctness of the original answer and the model's class and size. Our approach is model-agnostic and applicable to closed-source models since we only analyze the outputs, specifically the top K token probabilities available through many APIs. When top K probabilities are not accessible, we can approximate them by sampling from the LLM, and we provide insights on how quickly this approximation converges to the true probabilities. In our experiments, we show that querying models with elicitation questions yields features that are beneficial for various applications. We demonstrate that these features can train accurate predictors of model performance, often matching or surpassing linear predictors that require white box access. Additionally, our low-dimensional features lead to stronger generalization guarantees for the predictors. We also find that our sampling-based approximations closely align with the performance of models using true probabilities, indicating that our method is effective even without top K access. Furthermore, we explore the impact of question diversity, discovering that even unrelated natural language sequences can sometimes outperform specific elicitation questions. Beyond predicting LLM performance at the example level, our extracted representations are valuable for other applications, such as detecting when an LLM has been influenced by adversarial prompts. We show that our method can effectively identify adversarial influences in a black box manner and is robust to variations in system prompts. Lastly, we demonstrate that our approach can reliably differentiate between various model architectures and sizes, which is useful for evaluating the authenticity of models provided through closed-source APIs. Overall, our findings suggest that follow-up queries and interactions with a black box LLM API can yield useful features for predicting its behavior, sometimes matching the performance of analyzing activations. In the next section, we will discuss related work on predicting model performance, highlighting the challenges of interpreting deep neural networks and how our approach differs by focusing on instance-level performance using minimal labeled data. Section Summary. In this section, we discuss the challenges of understanding large language models, LLMs, and propose a method to predict their behavior using black box access by querying them with follow-up questions about their outputs. Our approach demonstrates that these queries can effectively extract useful features for predicting model performance, even outperforming traditional methods that require white box access to model internals. Section: Extracting features from neural networks. In this section, we explore how to extract features from neural networks, particularly focusing on language models. Many studies have investigated ways to obtain representations from these models. Some approaches train image classifiers to identify a small set of clear concepts, which can then be analyzed with a linear probe to create a classifier. However, We utilize the language model's understanding to extract features without needing additional training, allowing us to do this in a way that is not tied to specific tasks. Previous research has looked into how to derive useful representations for various applications, but our method is distinct. We aim to extract more compact, low-dimensional features that provide insights into the behavior of black box models. Some related work involves asking questions to identify when a model may be dishonest, but our focus is broader, as we seek to predict overall model behavior and performance. We also examine how well a language model can express its own uncertainty. Our follow-up questions prompt the model to evaluate its answers with yes or no, which relates to its ability to recognize what it knows and to express uncertainty in its decisions. While we primarily analyze the top probabilities from its responses to create our representations, other studies have looked at using confidence scores. Some research has suggested that iterative prompts can better capture different types of uncertainty, but our approach differs. We extract probabilities to train a simple, calibrated linear classifier that predicts model performance and audits models influenced by adversarial factors. We compare various uncertainty quantification methods, demonstrating the advantages of our follow-up query approach. Since we do not have access to the internal workings of a language model, we propose extracting useful features by asking follow-up questions about its outputs. This method is entirely black box, as we only consider the model's outputs, specifically the top probabilities for the next token. We use these features in simple linear classifiers for tasks like performance prediction. In cases where we cannot access the model's top probabilities, we analyze predictors trained on sampled approximations. To gather our black box representations, we prompt the model with numerous elicitation questions. We define a set of questions and consider a dataset where each entry consists of a sequence of tokens and a corresponding binary label indicating whether the model answered correctly. We denote the model's greedy response and construct our representation as a vector, where each dimension corresponds to the probability of a yes response based on the input question and the model's answer. Our elicitation questions, which include simple self-reflective inquiries, help us enrich our representations by generating additional follow-up questions. We find that around 50 questions yield strong performance. Alongside the probabilities from these questions, we also include pre- and post-confidence scores and the distribution of possible answers for the task. In our experiments with GPT models, we add the top 5 probabilities returned by the API. We then train a linear predictor to determine the label based on our feature vector. Section Summary. In this section, we explore methods to extract low-dimensional, interpretable features from language models by asking follow-up questions about their outputs, enabling us to predict model behavior and performance without needing access to the model's internals. We demonstrate that our approach, which includes eliciting probabilities and confidence scores, enhances the representation of model uncertainty and improves the performance of a linear classifier for various tasks. Section: Generating follow-up prompts. In this section, we outline how we generate follow-up prompts. To create our set of questions, we start with a few that focus on the model's confidence in its answers. We then use GPT-4 to produce a larger set of 40 questions. The specific questions and prompts used for generating these are detailed in the appendix. Previous research on lie detection suggests that a diverse range of questions can yield more informative representations from the language model than simply asking it about its answer directly. We observe that the nature of the question can influence the model's response, such as the likelihood of it saying yes, which may serve as a weak indicator of correctness. This concept is similar to weak learners in boosting or weak labelers in programmatic weak supervision. However, to keep our method flexible and not limited to specific types of questions, we treat these as abstract features for a linear predictor. We also recognize that future work could optimize these prompts to enhance the usability of the extracted representations, as discussed in earlier studies. A key advantage of our current method is its simplicity, functioning as a task-agnostic classifier. Optimizing these questions could risk overfitting, and analyzing the resulting predictors would require more complex methods to ensure valid generalization. Next, we address the analysis of finite samples from black box language models. Our method assumes we can access the top probabilities, but some models only provide API access without this information. In such cases, we can estimate these probabilities through high-temperature sampling. We provide a theoretical analysis of how this approximation affects our method's performance. We define our representation as a vector corresponding to the actual probability of the yes token. Without direct access to these probabilities, we use an approximation based on averaging samples. Previous work in logistic regression indicates that as the number of samples increases with the dataset size, the maximum likelihood estimator on the observed approximation yields a consistent, though biased, estimator. We present a result showing the convergence rate of this estimator. Essentially, our findings suggest that even without access to true probabilities, we can closely approximate them through sampling, provided the sample size grows at a controlled rate. In our experiments, we evaluate the effectiveness of these extracted representations in three key areas: predicting the performance of various language models on text classification and generation tasks, detecting adversarial influences on a model, and distinguishing between different model architectures. We refer to our approach as KRE, or question representation elicitation, and we provide code for replicating our experiments. For our baselines, we compare against several methods, including two strong baselines that assume access to more information than we do. These are REP-E, which extracts the hidden state of the model at the last token, and full logits, which uses the complete vocabulary distribution. Both methods are not applicable to black box models and serve as strong comparisons. For black box models, we approximate full logits with a sparse vector of the top probabilities if available. We also compare against a version of semantic uncertainty for closed-ended questions, which aims to quantify uncertainty by grouping similar tokens. This method does not apply to open-ended questions, so we only present results for open-source models. Additionally, we compare pre- and post-confidence scores, which reflect the probability of the yes token based on the model's confidence before and after seeing the response. Lastly, we look at the normalized probability distribution over potential answers, similar to prior work on in-context learning. These comparisons help us understand the performance improvements gained by incorporating additional elicitation queries. Section Summary. In this section, we describe our method for generating follow-up prompts to assess a model's confidence in its answers, utilizing both a small set of targeted questions and a larger set generated by GPT-4. We also analyze how approximating probabilities through sampling impacts our method's performance, demonstrating that our approach can effectively predict outcomes in various applications, even when working with black box language models. Section: Datasets and Models. In this section, we compare our method to baseline models across various open-ended and closed-ended question-answering tasks, including NQ, Squad, BoolQ, Wino Grande, hallucination detection, toxic comment identification, and common sense reasoning. We evaluate the performance of Llama 3 models of different sizes and OpenAI's GPT 3.5 and GPT-4o mini models. For text generation tasks, we use a greedy sampling approach to obtain answers. In the NQ dataset, we enhance prompts with 2 examples from the training set to help the models align better with the expected answer format. More details on our experiments can be found in the appendix. Our first evaluation focuses on predicting the performance of the language models on QA tasks. Accurately predicting performance is beneficial for resource allocation and identifying challenging tasks, especially in high-stakes situations where errors can have serious consequences. For open-ended tasks, we check if the model's answer is correct based on various metrics, such as exact matches on Squad and valid answers on NQ. For closed-ended tasks, we simply assess the binary correctness of the answers. We find that our method, KRE, significantly outperforms other approaches on open-ended tasks and often excels as a black box method on closed-ended tasks. We also compare KRE with other uncertainty quantification methods and find it consistently superior. Further results for other models are available in the appendix, showing similar trends. Next, we show that KRE can effectively differentiate between a clean language model and one influenced by adversarial prompts, which is essential for ensuring reliable AI systems. We conduct experiments on both QA and code generation tasks, using various adversarial and helpful prompts to train linear probes that can distinguish between them. Our results indicate that KRE can reliably identify when a model has been affected by adversarial prompts in both settings, outperforming or matching all other methods. We also explore the ability to distinguish between different model architectures based solely on their outputs. This capability is practical for detecting whether a less expensive model is being misrepresented through an API. Our experiments demonstrate that KRE can reliably classify different LLM architectures and sizes, with linear predictors achieving near-perfect classification, while other methods struggle. This suggests that different model sizes exhibit distinct output distributions, indicating that naive confidence scores are insufficient for differentiation. Finally, we present experiments that highlight the generality and transferability of classifiers trained on representations extracted via KRE to out-of-distribution settings. We compare KRE's performance when transferring from one QA dataset to another and from one Llama 3 model size to another. Across all tasks, KRE consistently shows the best transfer performance, making it the most effective approach for handling out-of-distribution scenarios without labeled data from the target task. Section Summary. In this section, we compare our approach, KRE, against various baselines across multiple QA tasks, demonstrating its superior performance in predicting model effectiveness, detecting adversarial influences, distinguishing between model architectures, and transferring representations across datasets. Our results indicate that KRE consistently outperforms other methods, highlighting its robustness and utility in enhancing AI system reliability. Section: Calibration. In this section, we discuss the calibration of our models, focusing on their accuracy at specific confidence thresholds. This is crucial in high-stakes situations where we want to rely on predictions from a language model only when we are confident in its accuracy. We find that predictors based on KRE have significantly lower expected calibration error compared to those using answer probabilities. We will provide additional results on other datasets in the appendix. Our method shows potential for creating well-calibrated predictors of language model performance, which is vital for their use in critical applications. We also highlight that our approach produces low-dimensional representations that can be paired with simple models to create strong performance predictors with tight generalization bounds. While previous work has explored bounds for linear models using features from pre-trained models, this has not been done for language models. Unlike earlier methods that extract representations from a model's penultimate layer, we utilize the features generated by a language model in response to language queries. We apply a specific pack-Bayes generalization bound for linear models, and we observe that our linear predictors trained on these representations offer better accuracy guarantees compared to baseline models. However, these results depend on the assumption that the representations from the language model are independent of the downstream task data, which can be verified through studies on data contamination or is valid for datasets released after the model's training, such as GPT 3.5. We also explore the performance of sampling from a closed-source language model, where we often lack access to top K probabilities. We conduct an experiment where we approximate the true probabilities by averaging a finite number of samples from the model's distribution. Our results show that using these approximations leads to only a minor drop in performance, indicating that our method is applicable even when we cannot access top K probabilities. Next, we investigate how the number of elicitation questions affects the information extracted in KRE. By randomly subsampling the number of elicitation questions, we find that our predictive performance improves as we increase the number of prompts, although the rate of improvement diminishes with more prompts. Similar trends are observed in other datasets, which we will detail in the appendix. This suggests that we can enhance our method's performance by using more elicitation questions, even those generated by the language model. We also compare the effectiveness of our specific elicitation questions, generated in a particular way, against random sequences of coherent natural language. Through an ablation study, we assess how these unrelated sequences impact the language model's distribution and their usefulness for downstream tasks. While using random sequences generally results in poorer performance than meaningful elicitation questions, we find that responses to these unrelated sequences can still provide valuable insights into the model's behavior. This indicates that we can generate additional follow-up prompts without needing them to be meaningful questions, thus maintaining diversity in our approach. We further examine the effects of different types of elicitation questions in the appendix, finding that human interpretable diversity does not always lead to more varied features from the language model.